Hi, my name is Lou Gramer. I'm presenting a poster for the AMS 101st Annual Meeting, January 2021. You see the full poster here with the key message highlighted right at the center of the poster. Let's dive into some. First of all, the title of the poster is Getting It Right at the End, Tropical Cyclone-Ocean Shelf Interaction. I want to acknowledge my very valuable co-authors, Jun Zhang, who, like me, is at CMUS in Miami, as well as NOAA's Atlantic Oceanographic and Meteorological Laboratory, Hurricane Research Division. Ghassan Alaka, who is a NOAA employee at HRD. Gopalakrishnan, who is the head of the modeling team at HRD. Hyunsuk Kim, who has recently transitioned to our laboratory in Miami. And Biju Thomas and Avichal Mehra from NOAA's Environmental Modeling Center in College Park, Maryland. The subject of the poster is that energy available to hurricanes near land depends on coastal ocean heat movement, and that this can be important for hurricane intensity forecasts. We'll move on to a brief introduction. Tropical cyclone intensities often change quickly near landfall. In 2020 in particular, we saw a number of instances in the Atlantic basin where storms intensified rapidly just prior to landfall. The energy available from the ocean for tropical cyclones evolves differently near coasts than it would in the open ocean. In other words, sea surface temperatures, or SSTs, evolve differently near coasts than they do over deeper water. Tropical cyclone winds in the open ocean drive vertical mixing at the base of the oceanic mixed layer. This is the dominant process of SST cooling by TCs over deep water. Near coasts, the circumstances are quite different, as we'll see. Here are the methods for this project. HWRF-B is the basin-scale hurricane weather research and forecasting model. It consists of an outer atmospheric domain spanning the East Pacific and Atlantic TC regions at 13.5 kilometers resolution, coupled to an ocean model called POM-TC at 9-kilometer resolution. Superimposed on the basin-wide domain are multiple storm-following high-resolution atmospheric nests, with outer nests at 4.5 kilometers and inner nests at 1.5 kilometer resolution. We construct an energy budget with the outputs from HWRF-B, showing the magnitude of heat fluxes, including at the sea surface, relative to frictional dissipation, potential energy, and kinetic energy change. We then look at how important shallow water interaction is to this overall energy budget and to changes in storm kinetic energy. A quick primer on the heat cycle in tropical cyclones is shown at upper right from a manual 2006. Air near the surface spirals in toward the storm center from points A to B in the diagram, gathering heat and moisture from the ocean below. Warm, moist air rises rapidly within the eye wall from points B to C in the figure. It then joins the outflow from the storm, points C to D at the top. Gradually, that air is returned to the environment, completing the cycle, as represented by motion from C to D. Finally, that air can subside back to the near surface boundary layer, as represented by the leg from D back to A. Now for processes affecting SST over the shelf and coastal ocean. TC winds moving parallel to a coastline can drive either coastal upwelling, which cools SST, or, as in the diagram at lower right, coastal downwelling. Downwelling has the effect of maintaining SST and potentially advecting warmer surface waters from offshore into the storm domain, maintaining or enhancing storm intensity. The integral energy balance equation that we use for this project is based on work by Trenberth, 1997, and Kato et al., 2016. On the left-hand side appear terms for storage and advection of sensible heat, Cp times temperature, and latent heat, L times humidity, as well as potential energy. In particular, in this equation, the surface geopotential phi sub s. Also on the left is a combined term for radiative and turbulent vertical fluxes at the top and bottom of the storm called AHF, a term for frictional energy dissipation at the sea surface, FD, and what we call a residual term, really just the lateral advection of potential energy out of the domain. Kinetic energy terms are isolated on the right. We'll look at one particular case study. This is a forecast cycle from Hurricane Sally in 2020. See on the left a group of forecast tracks, and the actual best track as assigned by the National Hurricane Center is shown in thick black. The particular forecast model, HWRF-B, that we used for this study is shown in orange with triangles. And the two tracks, you can see on the left-hand side, match each other pretty closely to within a few hours of landfall. This forecast track is not perfect, so it continues to the northwest when the best track makes a sudden right turn towards the northeast. But we'll be looking at the period of time where the storm was intensifying, both the observed best track and the forecast track. If you look on the right-hand side, the wind speed, this is the maximum 10-meter wind, observed in solid black, and again, with a number of models, including in particular HWRF-B, again, the dark red triangles. And in particular, the area that's circled here, you'll notice that the storm intensified very rapidly and was forecast also to intensify very rapidly within a period of about 12 hours. So the best track rapid intensification began around forecast hour 54, and the forecast rapid intensification actually began at about forecast hour 60. So a pretty good job done by the forecast model. And again, this included interaction with the shelf and the deeper ocean offshore, and we'll look at that in more detail. So here is the energy balance derived from this forecast run. In the graph at right, energy in terajoules is shown on the y-axis, and in the x-axis is forecast hour since the model initialization time on September 9th at 06 Zulu. The line in blue is the 6-hourly change in the kinetic energy integrated throughout the volume of the storm based on model wind speeds. The orange line is net vertical turbulent heat fluxes, accounting for both air-sea fluxes at the bottom and the outflow at the top, minus frictional dissipation. The difference between the two, shown as a third green line, represents a combination of advection terms for internal and kinetic energy and the residual, representing, again, advection of potential energy out of the storm domain boundary. Periods of rapid increase in peak surface wind are annotated by black horizontal lines, and periods of rapid weakening by red horizontal lines. This result shows that a significant portion of the energy from vertical fluxes is transformed pretty rapidly into kinetic energy, and so ultimately can enhance storm intensity. But there's also a substantial portion of it which persists as potential energy and which contributes to increases in internal energy, the moistening and warming of the air in the storm. So, what was the role of the coastal ocean in the intensification of this storm? So we have a sequence of 3 images showing the whole Gulf of Mexico. These are based on, again, HWRF-B model outputs. The color is latent heat flux from the ocean into the storm And the spatial pattern that becomes apparent between our forecast hour 42 on the left, 48 in the middle, and 66 on the right, the pattern shows that a significant fraction of that latent heat actually was transferred into the storm from the shallow water near the coast of Florida and Alabama, Mississippi, and Louisiana. We'll look at that in a little bit more detail. So this is the inner model domain for those same 3 forecast hours. Again, it's clear that a significant portion of the available energy for intensification of the storm as it approached landfall, again, the time is from left to right, separated by approximately 6 hours. As the storm approached landfall, a significant portion of the energy that went into the increase in kinetic energy in the storm, as well as other terms, was coming from the shallow ocean. And in particular, we'll see that a lot of it flowed into the storm at ocean depths between 50 and 150 meters. So what was happening to the ocean as Sally was transiting the northeastern part of the Gulf of Mexico? These 3 figures for forecast hour 48 have arrows showing ocean model currents at the surface and down to 100 meters depth. The National Hurricane Center best track of the storm is shown with a solid black outline, the HWRF-B forecast track with a dashed outline. The size of the storm, the radius of 34-knot winds, according to best track, is shown as a black circle, and the 34-knot wind radius, according to HWRF-B, is shown as a dashed circle. Highlighted with an orange dashed ellipse is the area of the Gulf Shelf to the right of and in front of the storm track, with an average water depth of between 50 and 150 meters, as indicated by the coast-following gray and dashed black lines. The left-hand panel shows significant convergence, that's negative divergence, in the ocean surface currents during the period of the storm's passage just offshore of the shelf in this region of shallow water. Looking at the elevation of the ocean surface in meters in the middle panel, we see a corresponding significant enhancement in surface elevation over that region of shallow shelf due to coastal Ekman convergence from the TC wind forcing. The result in terms of change in SST since the forecast began is shown in the right-hand panel. The change was essentially 0 over this shallow shelf region, as shown by the white areas over the shelf, despite the presence of the intensifying storm just offshore and the presence of 34-knot winds over the shelf itself for a period of over a day. This contradicts the usual intuition that during the passage of a storm, its wind field will force a cold wake in the ocean. In fact, a cold wake near the center of the storm can be seen here as a purple region in the lower right of the panel, indicating cooling of over 4 degrees Celsius. This was in the deeper water, but what was happening toward shore was a convergence of near-surface currents, increasing sea surface elevation, resulting in a barotropic cross-shore pressure gradient, and ultimately the maintenance of warmer SSTs over this region, despite the presence of tropical storm force winds there. In conclusion, in this case of Tropical Cyclone Sally, as in several other cases from 2020, it can be seen how modeling of processes over the shallow ocean can impact the energy balance of the storm and ultimately its intensity, particularly near landfall. That's it. Please refer to our project website at bottom center of the poster for more information on the near operational HWRF-B modeling system and our research with it. Thank you for your attention. This is an extra slide. If you've made it to the end of the poster presentation, you may be wondering, how commonly do the effects presented here actually occur? As it happens, they appear to be quite common. On this extra slide are figures showing the intensification of another 2020 storm, Laura, 13L, that spent time interacting with the ocean shelf and intensified near landfall. These panels show a similar pattern to Sally. Near-surface ocean currents converge on a shelf. Incipient downwelling maintains the SST as the storm's wind field approaches it, enhancing the availability of energy from air-sea fluxes. Other such examples of interest in 2020 included Hannah, Isaias, Delta, and Ada, while earlier examples we've studied include Dorian in 2019, Michael in 2018, and Irma in 2017.